All right, 4.6 part 2, solving rational inequalities. Example 4, we've got this rational inequality. Let's solve it algebraically. So what we can see here is that we have x-intercepts occurring at -1, at 3. We also have a vertical asymptote occurring at x equals 5. So that means on our number line, the idea here is you have x-intercept at -1, at 3, and then at 5 you got a vertical asymptote. I'm just going to go ahead and say, look at that sign analysis. We got a vertical asymptote at 5, but you can include values at 3 and -1, so we give those hard closed circles there. Keep that in mind because remember the idea here is that you want to show when the graph is greater than 0, so we actually don't want those values there. So that's something to be aware of. Actually, if you want to kind of do this in a different manner, you can actually say, since I don't want the values of -1 and 3, I'm going to go ahead and give those open circles, knowing that I should not include those values. So that's a way of doing it too. Okay, and then from here, you can again just do your sign analysis. You've got x plus 1. You've got x minus 3 squared, and you've got x minus 5. You can even do the denominator. Okay, so when you do this, you can just do the normal way. X plus 1 is a slope going up. It is negative until you reach -1, and then positive throughout, just like that. X minus 3 squared is positive everywhere. And then x minus 5, that is negative until you reach 5, and then positive throughout. Okay, so let's see our final signage. We've got negative, positive, negative. That is positive, negative, negative, and positive. Okay, so when we solve this algebraically, we are looking for values greater than 0. That is all the positive numbers. So there, there. So don't forget we don't need to include 3 because it is not greater than 0 at that point. That's when it's equal to 0. So we can say our answer is -infinity to -1. -1 is non-inclusive. Union, you start at the vertical asymptote at 5, non-inclusive, and you go up to infinity since that's where it is positive. All right, we can check our work. We can graph it. So as we graph it, let's see what we have. We have x-intercept at -1, at 3, and we have vertical asymptote at x equals 5. Okay, just like that. And what else are we missing? Anything else? I think that's it. Okay, so we already saw in our sign analysis, it is positive to left of -1, positive. And then it is negative until we reach 3. So it's coming down until we reach 3. And then, oh, it's a negative again. Let me redraw that. So basically, you're going to rebound off 3 like that, and then come back down. It's negative. So it'll go like that. There we go. Okay, and then it's positive everywhere else throughout. So because of that, it's just kind of going like this, maybe even up, doing something there. Okay, we probably have an oblique asymptote actually. Okay, so it's going up like that. Use a graphing utility to verify. You could do that on your own. Okay, feel free to just plug that in and examine your graph. All right, let's go on to the next one. So this one, you're graphing a system of equations almost. You've got f and g. To solve this algebraically, what we're going to do is we're going to put them both into our inequality. So what we have is x cubed minus 7x squared plus 4x plus 12 greater than 3x squared plus 7x. So all we've done so far is plug our functions into the inequality. And to solve this, you just want to combine everything into one equation. It's almost like solving a system of equations. Okay, so what we're going to do is subtract 3x squared on both sides, subtract 7x on both sides. Let's see what we get. We get x cubed minus 10x squared minus 3x plus 12 greater than 0. And so the idea here is you're kind of solving this almost like a regular equation. The idea is you need to look for those factors. Once you get all those factors, you'll then be able to say, I need to find those zeros, make them equal to a 0. Do your sign analysis with those factors, and then ultimately decide when do you have positive values, when do you have negative values, and that will give you your solution set. Okay, so that's the main idea. Let's go ahead and do that. So with this polynomial, it looks like we cannot factor, so we're going to have to resort to synthetic division. Let's go ahead and say, let's just try 1 and -1 first. So we have 1, 1, -10, -3. Hopefully this works. Please work, please work, please work. 1, 1, -9, -9. All right, sweet, it works. Okay, so we have, do I have space? I have space. So we have x minus 1 times x squared minus 9x minus 12, and this is when we're trying to find when it's greater than 0. 12, what do we have? 1 and 12, 3 and 4, 2 and 6. I don't think we can get 9. All right, so that means we have to resort to the quadratic formula then. So x is equal to negative b plus or minus the square root of b squared minus 4ac, negative 12, all over 2a. Okay, so we're going to get x is equal to 9 plus or minus the root of 81 plus 48, all over 2. I'm just going to use my calculator here. Bear with me. You can do it too yourself. Okay, we're getting 10.18 and negative 1.18. Okay, and then we also have the 0 of 1 as well. Okay, so we have x equals 1, n equals 10.18, and negative 1.18. So sign analysis says we have negative 1.18, and then 1 comes after that, and then 10.18 comes after that. All right, so plugging in numbers. I'm just going to plug in numbers. Let's say we plug in test values of negative 2. Let's do 0, 2, and 11. We'll do that. All right, so plugging in numbers, just going to plug in. What I'm going to do is I'm actually going to plug it in to this statement here and just see when that is greater than 0, basically. So just going to use my calculator here, plug it into this here. Okay, and I am using my graphing calculator and doing some of the techniques I showed you in class just to be able to get that answer easier. So getting positive 2, negative, and positive. Okay, so we have answers in, let's see, what do we have? What are we looking for? Find it when the polynomial is greater than 0. We don't want equal to, we only want greater than. So don't include your actual zeros, and positive would mean you want this section and this section. So we have basically negative 1.18 non-inclusive to 1 non-inclusive union 10.18 non-inclusive to infinity non-inclusive, and that'll be your answer there. Okay. We can verify work by graphing this, and so I've already gone through the liberty of plugging this into Desmos. You can see here. Feel free to just draw this on your paper. Basically, the idea here is you can see that the blue graph represents our x cubed function. The green graph represents the x squared function. And as we go back to the equation, the inequality, remember what we're looking for. When is the cubic greater than the square? So when we look at our graph, I'm going to go ahead and, let's see, can I take a picture here? Oh, I know. Screen right. Okay, when is the blue graph, which is this here, greater than the green graph? Basically, when is it above? And you can see that the blue is always above the green in this section here. And that's going to be the interval that we found. That was, I believe that was the negative 1.18. And then it went to, what did we say? I think it was the value of 1, negative 1.8 to 1. That was the first interval that we found right there, where that blue is above the green. You can see in this area the green is above the blue, so we don't want this section over here. As we go on, notice how green surpasses blue over here. And then eventually, you can see that blue is going up, the green is also going up. Notice how that blue is going up at a steeper rate than the green is, though. So eventually you're going to find that they intersect together, and where they intersect was giving us our second location, where the blue will overtake the green. Okay, so as I go back, you can even see that on the graph here. Where does that occur? Way up here. There. See at 10.18, there it is. That's when the blue has surpassed the green. We can see it right there. Blue is above the green. Okay, so that's basically just confirming the results that we had found. All right, so on to the last problem. All right, so here we go. So y is less than or equal to x cubed plus 2x squared. And we can see here this problem is a little different from the others in that we actually see two variables here. Very similar to what we saw in the previous problem. There were two variables, a y equals, but we ended up turning it into a one variable equation. In our case here, we don't have that option. We can't turn it into one variable. So do be aware, when you are graphing with two variables, it does work a little bit differently. Let's see how that's done. We're going to go ahead and factor, so we get x squared times x plus 2, and therefore we can see zeros occur at 0 and also at negative 2. So graphing this, let's just graph this in terms of every 2 units is a length of 1. So 1, 2, 3, 1, 2, 3. Notice how we're having this on the coordinate plane, right? Because we have two variables. And with two variables, we have intercepts at 0, 0. Oh, sorry, wrong one. 0, 0. And also at negative 2, 0. Zero is a double root. It bounces. Negative 2 is a single root that just goes through. And so for that reason, let's see what we have. An x cubed. 1x cubed means as a positive odd degree, you should have an end behavior that goes from down to up. So we're going down, going through negative 2. It's a single root, and then it'll come up. You have to then go back to your double root. It'll rebound off 0 because it's a double root, and then come up. Now notice how I am drawing my graph as a solid line. One thing to remember from your Algebra 1 class is when you look at this inequality, remember when you see less than or equal to, or even greater than or equal to, any one of those, you are graphing with a solid line. But if you have greater than or less than, then you are graphing with a dotted line. This is only for two variable equations. Okay, so because we have equal to, I'm going to give it a solid line here. And the last thing you want to do, make sure you test. You have to show your test of a point. You show a test point that is not on the line. So for example, I'm going to test the point 2, 0. I could test 2, 0. I could test 3, 1. I can test any point anywhere. Honestly, it doesn't really matter. I can even test over here. It doesn't matter. But the idea here is that when you test a value, you plug it into your equation. So 0 is the y, less than or equal to 2 squared times 2 plus 2. I'm just plugging in my x value. Is 0 less than or equal to 4 times 4, which is 16? Is 0 less than or equal to 16? For sure. That is a true statement. So therefore, we're saying that 2, 0 is a solution to our inequality. And if 2, 0 is a solution, then so are all these other points here. And what that means is we're going to shade everything that is on this side of our line, including this little hump here. Make sure you include that, right? And you want to shade everything on this side of the line, just like that. And that's going to represent your entire solution set. We can't write that as an interval notation because you have two variables. It's not just the x value. And so your answer, your solution, is technically just the graph itself. And you just graph it like that. Okay? That'll do it. Okay? If you have any questions, feel free to let me know.